The Center for Quantum Philosophy of Geneva aims to promote the discussion on the philosophical and scientific challenges raised by the interpretation of the quantum theory. The Center addresses itself to people who think that quantum theory is not only a practical summary of mathematical recipes, but that it is now an integral part of knowledge and culture. After the talk by Herbig Chopper on the concept of particle a month ago, we want to reflect today on two other fundamental principles of quantum theory, and determinism and non-locality. Everyone who reads the rigorous book of John Bell, Speakable and Unspeakable in Quantum Mechanics, wants to ask the author, are both determinism and non-locality necessary for a coherent physical theory, or only one of these principles, and in this case which, or neither of them? We are most grateful to Professor Bell for having agreed to discuss with us these questions.
Imagine that this is a metal grid made of some very tough metal. And I am shooting bullets at it. Sometimes the bullet will hit the metal and be stopped, and sometimes it will go through the hole. Now imagine that that is made on a microscopic scale, so that I cannot see with my eyes or even with my instruments, that it is made like that some parts are transparent and some parts are opaque. Then what would happen when I shoot my little bullets would be sometimes they would go through and sometimes not. And I would have a situation of unpredictability. My experiment would sometimes give one result, pass, and sometimes another result, stop. And the classical physicists would understand this situation by saying that the unpredictability arises from the lack of control. That although I think I am doing the same experiment each time, I'm not doing the same experiment each time, because there are little things which I am not reproducing sufficiently accurately from one time to the next. And for a classical physicist, or let's say a 19th century physicist, unpredictability simply meant lack of control. So the unpredictability was in no way synonymous with indeterminism. For that classical physicist, the unpredictability was a reflection of human weakness, and nature might very well be perfectly deterministic. Now, we have a situation a bit like that when we think of the photons streaming up from this lamp and coming up here and being reflected towards the blackboard. If I put in some absorbing material, not all the photons get through. And if you did the experiment one photon at a time, you would find that sometimes the result of the experiment would be passed, sometimes it would be stopped. And it would be quite unpredictable, which was the case. The classical physicists say, we don't get the result different because we know everything controls things. There is something to control in this experiment. But the founding fathers of quantum mechanics did not say that. They said, we are confronted here with the case of indeterminism. Now, when I read history, it always amazes me that the founding fathers could come so confidently to that conclusion. Up till then, the tradition in physics was that if something was unpredictable, it was because it had not been fully controlled. And for me, the natural assumption would be that the situation with photons is like this situation here. And that was also the natural photon. For Einstein, we say God does not play God. For him, it was almost an article of faith that nature is lawful, and if we could not control it, it was our fault. And so he contemplated that the description given by quantum mechanics was incomplete. It should be supplemented by hypothetical hidden variables, which we do not know just by inspection, but we will have to make theories about. And that when these hidden variables were found, at least conceptually, that we would again see that nature was perfectly lawful, and that we would have determinism. Now, the piece of absorber that I put there is not just any old material, it's actually polarizing material. And the photons that get through a polarizing material have the property that they cannot get through a second piece of the same material if it is oriented at right angles to the first. Whereas if it is oriented parallel to the first, it gets through again. So that is a property of photons, that they have polarization, which can be detected by such pieces of material, and that plays a role in the sequel to what I have to say. Now, at first, this was simply a working hypothesis of Einstein and for a few other die-hard classical 19th century physicists. But in 1935, he invented an extremely powerful argument for this position, based on another hypothesis which most people who have not met these phenomena before would accept, the hypothesis of no action at a distance, which is sometimes called local causality or just locality. And he said that there are situations where this hypothesis implies determinism. So in this argument, determinism was no longer a hypothesis but a theorem, but with this as the axiom. Now the situation that he, and later on in a more simple example, David Bohm, the situation which he drew attention to was this. You can make, in a way that I will not go into in detail, twin photons. You can have a source which, when you press the button, emits a photon going into this diagram and another photon coming out. And you can see whether these photons do or do not pass through pieces of polarization detecting material. And the twin photon source has the character that whenever the photon passes here, its twin passes there, and whenever this one does not pass here, the twin does not pass there. That's a feature of this particular source. Such sources exist according to quantum mechanics and have been built experimentally. And that is true no matter which way these things are oriented, provided they are oriented in the same way. Now, this is a very powerful argument against the idea that the passage of this photon through that polarizer is a matter of pure chance. If it was determined by a die being cast over here, this was determined by a die being cast over here, how could they possibly always agree either to pass or not to pass on a given occasion? The situation here is rather like one which is extremely interesting to biologists when you have identical human twins. I believe that all babies are born with blue eyes, but some of them then turn brown. And you might think that was a matter of chance. It's interesting to take bets on whether brown or blue is going to come. But it's not a natural chance. We know that from the phenomenon of identical twins. But even if they are separated before their eyes acquire their final color, if one turns brown, so does the other, and if one turns blue, so does the other, and we don't think, oh, what a mysterious distant correlation. We say that's genetics. And similarly here, a reasonable assumption for any reasonable person is that we are concerned here with a case of genetics. That these photons, unknown to us, carry some small packets of information. The same information in the two cases, which dictates that when they meet the same circumstances, they will behave in the same way. And that was the Einstein philosophy was an argument from no action at a distance to determinism. If you didn't want to accept that hypothesis of determinism, I think you are obliged to accept that in some way things can agree at a distance without any explanation. And that for Einstein would have been an objectionable action at a distance. Now, for Einstein then quantum mechanics was incomplete. The formalism that we are taught is not the whole story. The genes are missing. It would be like biology without genes, where things just happen by chance, and it is quite mysterious that sometimes they happen in the same way to identical twins. He supposed, therefore, that there must be some variables that we don't know about, which are not under our control, analogous to the genes. And they explained these correlations at a distance, without causation at a distance, because the causation was transmitted from the source to these objects. Einstein said originally God does not play dice, but in this argument it was no longer an assertion by itself, it was an inference from the assumption of no action at a distance. And in later years, Einstein was much more concerned about the fact that quantum mechanics was not explicitly free from action at a distance than he was concerned about determinism as such. Now it is a great irony that this argument, which I think was an extremely powerful argument, and which the people of the day should have accepted, that this argument boomeranged on him and became an extremely powerful argument against his own position. Now that came about as follows. We did that experiment. I described the results of that experiment with parallel polarizers. But of course you can also do it with off-parallel polarizers. Now let's start with the parallel case. And then suppose we turn this through 30 degrees. We will no longer get perfect agreement. Sometimes a photon will pass here and its twin will not pass there, and vice versa. And quantum mechanics gives a formula for the degree of discordance that creeps in when you turn such a device. Now we could turn the other device instead, and there would be some discordance. And we could turn both of them, and there would be another discordance. Now there's a simple relation between those three situations that I have described, turning this one, turning that one, or turning both. And it's the following. Let n be the number of cases in which you have disagreement on the two sides, a yes and a no, or a no and a yes. When the two polarizers are both at 0 degrees, there is no discordance. I always get yes, yes, or no, no, never yes, no, or no, no. If I now consider the case where both are turned, one minus 30 degrees and the other plus 30 degrees, then it's easy to see that on the genetic hypothesis that this number must be less than or equal to the discordance with just one term plus the discordance with only the other term. And that is indeed easy to see because the programming of this device must be such that a yes, some yeses are replaced by no's, and some no's by yeses when I turn it. Similarly, when I turn that, some no's are replaced by yeses and some yeses by no's. But now in this case, every change in the programming introduces a discordance, because originally I had perfect concordance, yes, yes, and no, no. So every change here introduces a discordance. Every change there introduces a discordance, but not every change here introduces a discordance, because there may be compensating changes in the program on the two sides. A yes may turn to a no, but a no may turn to a yes, and again you will have agreement. And therefore, the amount of discordance with the two movements is less than or equal to the amount of discordance with both movements. Now, if you calculate that according to quantum mechanics, that just isn't so. I don't remember. I think I remember the exact numbers, but this turns out to be 3/8 as a fraction of the total number of trials. That 3/8 of them will be discordant. And here it is 2/8. Here it is 2/8. That's not right. It must be something like that. One. But this is a fact that quantum mechanical predictions and experiments, insofar as they have been done, do not agree with that inequality. And that's just a brutal fact of nature. The genetic hypothesis, which seems absolutely compelling for parallel devices, simply doesn't work for non-parallel devices. You can't get away with the genetic hypothesis. And therefore, the Einsteinian argument failed. No action at a distance led you to determinism in the case of parallel polarizers, but determinism in the case of off-parallel polarizers leads you back to action at distance. Now, in my opinion, in answer to the question that you posed at the beginning, I don't know. This phrase is too strong and active an assertion. I cannot say that action at a distance is required in physics. But I can say that you cannot get away with no action at a distance. You cannot separate off what happens in one place and what happens in another. Somehow they have to be described and explained jointly. Well, that's just the fact of the situation. The Einstein program failed. That's too bad for Einstein, but should we worry about that? Super. Now, there are three replies to the question, so what? One is that the whole idea of action at your distance is very repugnant to physicists. If I were speaking for an hour or half an hour, I would bombard you with quotations from Newton, and Einstein, and Bohr, and all the other great men, telling you how unthinkable it is that by doing something here, we can change the situation in a remote place. I think that the founding fathers of quantum mechanics did not so much meet Einstein's arguments about the desirability of no action at distance as they looked away. The whole idea that either there might be determinism or action at a distance was so repugnant to them that they looked away. Well, that's tradition, and we have to learn in life sometimes to learn new traditions. And it might be that we have to learn to accept not so much action at a distance, but the inadequacy of no action at a distance. There are two more professional reasons for being discontented with the situation. Now, one is relativity. According to relativity, the notion of simultaneity is relative. And events which are simultaneous for one observer are not simultaneous for another. So it does not make sense for very distant situations to say that one event has occurred before or after another. So if we allow the result at one of these experimental setups to depend on what an experimenter does at the other, we have a puzzle, because we would not like what he does here to have an effect there before it is done here. But if I say that this is affecting that, I can find some observer for whom this comes after that. So if I set up a traditional causal model, in which the cause effects are allowed to be non-local in the sense of propagating instantaneously over large distances, in some frame of reference, the cause will come before the effect. So I have to be more subtle than that somehow. I have to find some way of devising a situation which allows something somehow to go from one place to another very quickly, but without being in conflict with special relativity. And that has not been done. We have the statistical predictions of quantum mechanics, and they seem to be right. The correlations seem to cry out for an explanation, and we don't have one. The other reason is no signals. It is a fact that I cannot use whatever this non-local connection is to send signals. When you look at what quantum mechanics predicts, it predicts so long as you look at just one side or other of this experiment, you will simply have no information about what is happening in the other place. No matter what that other fellow does with his equipment, you will not notice anything funny happening in your side. As an analogy of that, I could say, supposing we were tossing coins, I here and one of you people down here, and supposing I had the power to say that your coin will turn in extra time before it falls on the table. Now you're looking at your coins and you see heads, tails, and you don't know when I have exercised my power to turn it once more, because you didn't know whether it was going to fall heads or tails. So we have the curious situation that to explain the correlations between my results and yours, I have to invoke some such mysterious power, but it is one which I absolutely cannot use to send you a message. I got here a demonstration of that. This is a computer simulation of such an experiment in which people are calling heads and tails. And when it comes up heads, I have written H, and for tails I have written a blank so that you can see it from where it's sitting. And there are a whole series of random heads and tails. Now, at some point I exercise my power, my remote power to turn a head into a tail. And here's the result. So somewhere in there, I have done something to the random code, namely exchange heads for tails. But you absolutely cannot see that. This message, as far as you're concerned, is as meaningless as the next. And it's only if you have two copies of that that you can compare, that you can see that something funny. That curious situation has inspired musical composition. There's a musical composition called the Bell's Theorem Blues. And I'm not going to sing it, but I'll say the words. Dr. Bell say we connected, he called me on the phone, but if we really together, baby, how come I feel so all alone? And that is the dilemma. We are led by analyzing this situation to seem that somehow distant things are connected. or at least not disconnected. And yet we do not feel that we are connected up to the rest of the world. So any resolution of this situation, I think, you cannot just say, oh, nature is like that. I think you must find a picture in which the perfect correlations are natural without implying determinism, because that leads you back to non-locality. And also in which this independence, as far as our individual experiences goes, our independence of the rest of the world, is also natural. So the connections have to be very subtle. And I have told you all that I know about them. Thank you.
Thank you. Well, for the times, I think we have now a lot of questions, and please you can ask what you want. So let me start. Can I come back to the very beginning, the difference between unpredictability and undeterminate? Well, the question is what you call lack of control. In quantum mechanics, in the end, it's until the principle which says you cannot get initial conditions which you know at any level of precision you want. The question, doesn't that exist already in classical physics? Even in classical physics, not talking now about crude experimental difficulties. And we know now that chaotic theories, that you might have branching points and so on. So even infinitesimal change of initial conditions might change the outcome. So is there really this big difference between classical physics and quantum physics as usually mentioned? And to mention another point there, action at distance. The old Newtonian gravitational theory was certainly action at distance. At a certain time, in classical physics, the question whether you called it action at distance or local actions did not matter at all, because it was just a question whether you expressed the laws in integral form or in differential form. Now, of course, we would say it is a wave. Still, we have found gravitational waves. So, from the point of view of classical physics, you would say the distinction between action at distance or local action doesn't matter. It's only different mathematical formulation. And only in quantum mechanics then suddenly the local action became so important. Why is that?
Okay, well, there were several questions there, and I don't know that I remember all of them. But presumably you will. The first thing is the difference between classical and quantum mechanics. I think there is a big difference. And I think that the recent fuss about chaos in classical mechanics has concealed this point. For example, people tend to say, oh, but also in classical physics, an infinitesimal change can make a big difference. But it's not actually so. I think that in classical physics, so long as you work with finite times, an infinitesimal change makes only an infinitesimal difference. Now it's true that if you go for infinite time, that you can have situations in which an infinitesimal change will at infinite time make a big difference, but not at finite times. In classical mechanics, however complicated the system, at any finite time, the result depends continuously on the initial conditions. People get intimidated by the fact that, oh, the sensitivity is terribly...
Is it true only for closed systems? Is it open systems?
Well, closed systems, yes. For open systems, what is outside is certainly unpredictable by definition, because I have excluded it from my knowledge. But for the fuss about chaos in classical mechanics nowadays is about closed systems. And they try to intimidate you with the idea that, oh, tiny changes can have big effects. But it is nevertheless true, still, that infinitesimal changes have infinitesimal effects at any finite time. So that although I cannot personally control the initial conditions with the precision that would enable me to predict the weather next year, it is nevertheless perfectly conceivable and a legitimate hypothesis that the equations are quite deterministic in character. And 19th century classical physics was like that, and 20th century quantum physics is not like that, according to the orthodox accounts.
I want to mention, but I think the difference is in classical physics one was treating all with linear equations. Apparently if you take non-linear equations, it's a question whether that's still true.
No, I don't agree with you. Classical equations are not linear. If you look at Newton's equation for the motion of a planet, m c to r t squared is equal to 9. Now we're going to sign minus m1 into divided by r1 minus r2, which is not in the least to me. And the equations that people are investigating nowadays under the heading of classical chaos. They could treat that, except that it is too complicated for them. But I'm quite sure that if they could take half a dozen particles and follow this equation, they will find what they call chaotic results. People are even telling how they use scientists. They now think that the solar system is chaotic in the sense that for very, very long times, very, very small changes in initial conditions will be decisive. But it remains true that infinitesimal changes will have infinitesimal consequences of finite time.
Perhaps on this...
There was a second part
yes.
question. You want to say something about it? And that was that Newton's gravitational theory was, in a way, and it is a nice paradox that Newton made his theory in that way, but he apologized for it. And there's a quite famous apology which he wrote, I think, in a letter to the philosopher Bentham. He said, "But one body may act upon another at a distance through a vacuum without the mediation of anything else is to me so great an absurdity that I believe no man who has in philosophical matters any competent faculty of thinking can ever fall into it."
But you did.
He said it was provisional. At the moment he had to put forward his hypothesis of attraction without explanation and use it as a way of getting agreement with the phenomena. But you see, he was not happy with that. And if anybody had said that's the final word on this matter, you see, he would have been thrown out of the faculty.
On this line of the question, with Gödel's theory, we have learned that there always will be questions in arithmetic that could be undecidable, that is, unsolvable by mathematical reasoning. Non-locality seems to suggest that there are also questions which could, in principle, be answered by way of mathematical reasoning, but that in fact cannot be answered because information about what is going on in regions far away from us is not available to us. What do you think? Is correct to think this way?
I don't know. I mean, you gave your thesis very briefly, and so I cannot judge basically whether you are correct or incorrect. But I do not myself think it is right to use the words Gödel theorem in this discussion. I don't see a connection, except insofar as both subjects are very difficult to us. But I think, you see, with Gödel's theorem, we have some kind of permanent boundary to the possibilities of systematic reasoning. But here, I think we have a temporary confusion. It's true that it is 60 years old, but on the scale of what I hope will be human existence, that's a very small time. And I think that the problems and puzzles that we are dealing with here will be cleared up. And we will look back on them with the same kind of superiority. Our descendants will look back on us with the same kind of superiority as we now are tempted to feel when we look at people in the late 19th century who worried about the ether and Michelson-Morley connection. The puzzles seemed insoluble to them. And came Einstein in 1905, and now every schoolboy learns it and feels I was superior to those old guys. Now, it's my feeling that all this action at a distance and no action at a distance business will go the same way. But someone will come up with the answer, with a reasonable way of looking at these things. If we are lucky, it will lead to some big new development, like the theory of relativity. Maybe someone will just point out that we were being rather silly, and it won't lead to a big new development. But anyway, I believe the question will be resolved. I do not think the question raised by Gödel will be resolved.
It seems that from what you have shown that the concept of an isolated system is appearing. Nothing is isolated anymore from the rest of the universe. In general, I know that in classical physics you can think that the influences from outside, the outside world, you can reduce to as small as you want. Is that still the situation?
Well, conceptually, you could reduce them as small as you like, but of course we can't declare that Jupiter does not exist. And so long as it does exist, it will affect the orbit of the Earth. And even the way this piece of chalk falls, a little bit, the chalk falls only roughly the way Galileo said. And to some extent, it feels the gravitational field of Jupiter and of the God Nebula and God knows what. And I can't switch those off.
But how far are we allowed now to describe anything without taking the whole universe into account?
Well, first of all, strictly speaking, you never were allowed to do that. It was always a rough procedure that for rough work we can neglect much of the universe. But when we looked at what our equations said, Newton's equations include Jupiter's gravitational field acting on this bit of chalk. So that when we looked at what our equations said, we had to remember the rest of the world. And I think it's about the same. If you are interested only in a limited part of the world, then in quantum mechanics you use a so-called density matrix, which kind of averages over the rest of the world. And then the density matrix has an equation evolving for itself and not mentioning the rest of the world. But you still have to admit that if you wanted as much precision as the theory could possibly yield, you just have to put the rest of the world back in. What I think is novel is that Einstein gave us a way of switching off the rest of the world outside the light cone. You could say that, yes, the rest of the world is going to have an effect, but that effect will not arrive before light could propagate. So that was a way of dividing the world into bits which are relevant and bits which could not be relevant. And that we don't have anymore.
That is a very important affirmation.
Oh, sorry, does that mean that you say relativity and quantum mechanics are not compatible?
No, I can't say that because I think somebody will find the way of saying that they are compatible. But I haven't seen it yet. For me, it's very hard to put them together. But I think somebody will put them together, and we'll just see that my imagination was too too limited. Well, as the people in that department work at present, they are not coming to this question, because the superstring is still formulated within traditional quantum mechanics, and you still have the superposition principle, which is really the root of all these things. But it could be that as they go further into that, they find that it just won't work along the traditional lines, and at some point they'll have to give up the superposition principle. Now there are hints in that direction. You occasionally see papers from over there called How Wormholes Reduce the Wave Function.
In a way, the pity that there are no hidden variables.
The pity.
Situation simpler.
Well, I don't know that there are no hidden variables. What we said there was that hidden variables cannot restore locality. But there was still a consideration that I began with, that the classical physicist still thinks that if repeating the experiment gives different answers, he has not quite repeated the experiment. And you can have non-local determinism, non-local hidden variables. So I could imagine a situation where we do add hidden variables. We do have again determinism, but not predictability, because we want to be smart enough to get things with sufficient precision. But we would again have determinism, and it would be non-local. We would see that in some way distant things were connected, and yet not in a way that we could get hold of to send messages.
But if there are hidden variables, somehow we are back in classical mechanics.
Well, it depends on what you call classical mechanics. You won't be back with the mechanics of Einstein, with the light cone neatly separating what is relevant and what is irrelevant. But you would be back with classical mechanics in the sense that you would have some equations, presumably integral rather than differential equations, and the equations would tell you what is going to happen. Whereas in quantum mechanics it's perfectly obscure whether we have a theory like that. In fact, we don't have a theory like that.
Well, but it seems if one admits the principle of free experimentation,
Yes.
that seems important.
Right.
Then Bell theorem holds. Is it possible to formulate this result in this way? In a world in which there are human free actions, either action at a distance, in this sense, exists, or we must accept that correlated events do not have any rational explanation.
I think that's...
Do you think that?
Yeah. I would not sign that.
Yes.
But certainly it sounds okay what you said. That's the kind of way I think also.
But it is important to say that Bell theorems has something to do with free experimentation.
That's not what you said.
Yeah.
So,
Well,
because you in your
yes.
what you said,
If
the free action was that hypothesis, and now you're trying to turn it into a theorem.
No, yeah.
Could you repeat what you said?
I think if one admits the principle of free experimentation, Bell theorem holds. And my question is possible to formulate this result in this way? In a world in which there are human free actions, either action at a distance exists, or we must accept that correlated events do not have any rational explanation.
What means free experimentation and free human action?
Well, free experimentation is the fact that there is in the science of what Professor Bell says in his book, no superdeterminism, in the kind that when I am arranging the setups, this action is not determined from the beginning of the work. Because if we admit this superdeterminism, then you can't infer about that's correct.
That's correct. It comes into the analysis when I turn one of these polarizers, I assume that I can consider the same hidden variables in the turned position or in the unturned position. But if my choice was itself determined by the hidden variables, the argument would fail at that point. So I have assumed that there is something outside my theory which is quite free, which is not dictated by the parameters, the variables in the theory. Now, it is a fact that if I give that up, I have no theorem. But I myself do not think it's a very essential point in the following sense that you know that there are, if you have random number generators on a computer, you could have a computer here generating random numbers and another one over there with a different program generating random numbers. And strictly speaking, they are determined what comes out. But for somebody who doesn't know the program, it's unpredictable what comes out. And they are self-determined, so that they have nothing to do with the hidden variables that are determining whether the photons do or do not go through polarizers. So I think that that is enough freedom, the freedom of random number generators. But that's not a theorem, because when you set a random number generator going, you have to pick the program. And maybe your choice of program would be determined by the hidden variables in your experimental setup. So you have to be very far-fetched to make this the escape line.
But that is, in fact, I was going to think in the same line about something came to my mind when I saw your computer example. There is, I don't know how it is treated in information theory, but when you have an encrypted text that carries no information, zero information, when you usually have the key for it, then the information becomes complete.
Right.
It's something very, very similar, I have the impression. But I don't know, in information theory, how does it treat it in encrypted text?
Oh, I don't know enough about information theory, but I remember that the information which a message contains is somehow related with the surprise character of the sequence. If you have something which is pretty random, it has no information. But if you find that the typical run of heads was 100 rather than 10, then you would say that's surprising, and you would assume that somebody is sending you a message. So the measure of information in the message is related to the surprisingness of the sequence that you get. And of course, whether something is surprising or not depends on how much you know already. And if you look at either of the two messages which I displayed, you would see no information. But when I put them together, it's clear there is information. I don't know how information theorists would handle that. That they can, but I don't know whether they can.
I have a lot of questions. But is it correct to say that indeterminism is not a necessary condition for a coherent quantum theory?
I would agree with that, yes.
Okay. But quantum theory is not incompatible with indeterminism. Or quantum theory is compatible with indeterminism.
I believe that quantum theory is compatible both with determinism and with indeterminism.
With both?
With both.
Yes, okay, all right.
Depending on locality and non-locality.
That's right. If it's deterministic, well, I think it has to be non-local, whether it's deterministic or indeterministic. I think you're stuck with the non-locality. I don't know any conception of locality which works with quantum mechanics. So I think we're stuck with non-locality. Whether we're stuck with determinism or indeterminism is another question. I know that if you didn't worry about Lorentz invariance, you can make explicit deterministic models which agree with all the experiments. But they're not Lorentz invariant. They have an ether in them. And that's hard to swallow. It may be that Lorentz invariance plus quantum mechanics is incompatible with determinism. But I don't know that. It's a possibility.
I mean, doesn't the trouble maybe come from the fact that we only consider special relativity? Wouldn't the things change?
They change a lot. You are right.
General relativity.
You are right, and I consider only special relativity usually just because I don't feel strong enough to face general relativity. But as soon as the space-time metric is itself quantized, you have big new doubts, because what is the light cone?
Because I mean, I would say maybe all the trouble comes from special relativity, which to my mind is anyway only a frame and doesn't contain any physics.
Right.
For instance, if you say that the action is at a distance, this is not possible. Well, you mentioned then with relativity one gets into trouble, but one had the trouble with the ether. Special relativity has abolished the ether, but what is producing the action now? So that you can get only by field theories, where you then have field quanta, which in case of gravitation you need the graviton, which means you have to quantize also gravitation. So I think to solve the problem, one probably has to go to general relativity and not stick to special. Maybe all, I don't know, but it could be that all the difficulties would disappear if you would forget special relativity.
Well, I certainly agree with you that we should be thinking in terms of general relativity. I think all the difficulties may disappear, but not at once. There are quite a number of people who have tried to combine general relativity with quantum theory. Never mind about hidden variables. And it's a very difficult thing to do.
But I thought the big success of the super gravitation, super strings, is that they've shown that in principle they exist theories.
Well,
mathematically all right.
Well, again, they have oversold their message to the general public, I would say. When you press them, you find that whereas they are announcing a theory of everything, they only have theories of S-matrix elements. That's to say, bodies come in from infinity, and they say nothing until they go out again at infinity. But we don't live at infinity. And in order to make a serious theory, including gravity, it must not be an S-matrix theory, but a field theory, which discusses things at finite times and places, and they can't do it. They have tried very hard and given up. So string theory is not in a state where you could bring it into this discussion.
But I thought they've shown that in principle you can have a theory which combines relativity and quantum mechanics without avoiding...
For the calculation of S-matrix elements. Right. Well, they couldn't even calculate the precession of the perihelion of Mercury with their theory, because it's only formulated for S-matrix elements.
Okay,
so they can discuss experiments that have never been done, like the Compton effect with gravitons. Well, that can be. They may, but what I'm saying is that the difficulties don't disappear today. I agree with you that it is right to think that you may be wrong in trying to solve your problems in too narrow a box when you know that there are other problems in other boxes. And there are some people who do have the courage to work with that as their motivation. And Roger Penrose, for example, he has just written a fat book in which that is the main message, that there are deep problems in quantum mechanics, and there are also deep problems in the cosmology and in the theory of the gravitational field. And for him, they are all the same problems.
But I'm not able to understand quantum gravity, therefore I would prefer another way, but do you see any other approach which could lead to a solution of the problems than supergravity?
Well, that's an area that I haven't gone in technically. I only know about the quantum theory of gravity by overhearing it. I've never looked at it myself.
Do you see any other approach?
Well, you see, I hardly even see that approach. So I don't see another one. I think all that is, certainly in my mind, it's in a very shifty state. and to declare that there is only one way or that there is no way and so on. I couldn't do that. It's just something which is going on, and a problem which has not yet been solved, but which may be solved.
But it seems, in this approach, it seems also big difficulties present, because these approaches are working with metrical mathematics. They are assuming in the mathematics, on the mathematics level, perfect coordinate systems. And therefore, they are assuming also perfect clocks and perfect meter sticks. But the idea of a perfect clock and of a perfect meter stick is not very solid, it seems. In some way, we should have, on the mathematical level, a non-metrical theory, a theory in which the metric is not so important. What is your opinion?
Well, I don't, again, have a clear opinion, but this is again partly the answer to the question why I stick to special relativity. I think that we are not concerned with small effects here. This inequality is not just a little bit violated, it's grossly violated. In a certain way of putting it, it is violated by a factor of the square root of 2, possibly by 40%. So small doubts about your clocks are not going to help you. So the sort of things that you would most expect to come into play when you go to general relativity and remember that the metric is not given but is part of the dynamic, they don't look to me promising. I think you need a big effect, and therefore you need some big shift of viewpoint even before you go to general relativity and quantize the metric.
So as you allow for non-local action, then it's much easier than many bodies influence one. So then could we speak about a force which is not one but several? I mean, something which appears when several conditions apply, but not only one. So then we will come to a situation very similar to a neural network, in which each network is influenced by the rest of the network. And then some concepts emerge which are not related with the peak of each neuron in the network, but it's something, a phenomena which appears about the relationship among the whole set.
Well, there the point that I would like to make is that a neural network is a classical system. It's complicated, but it's classical. One neuron does not change another until it has fired and until it has propagated through intermediate neurons and so on. So that's a big, complicated classical system which they simulate by computers, which are classical objects. So I don't think that would get the essence of this non-locality problem. It could be important for other aspects of quantum mechanics, like the apparent indeterminism. The apparent indeterminism might be due to hidden complexity, including the fact that everything interacts with everything else and is not really isolated. But the non-locality problem is something else. And I don't think any amount of classical complexity will account for that. These correlations they are not, the mystery of them cannot be solved by complication.
There is one question of language maybe which confuses me. When we sometimes there is the word interaction, action at a distance,
Right.
or causality.
Right.
I think in general this involves a force or transfer of energy,
Right.
so a signal.
Right.
And then you say that is no signal. There is information involved, but not energy transfer. Is it right?
There is no energy transfer and there is no information transfer either. That's why I'm always embarrassed by the word action. And so I step back from asserting that there is action at a distance. And I say only that you cannot get away with locality. You cannot explain things by events in their neighborhood. But I am careful not to assert that there is action at a distance.
But I was hearing everything interacts with everything that is not interact.
Well,
Correlated with.
let's change it and say that you cannot account for anything without taking into account everything. And then I have avoided the word interaction. It's true, the word action brings up in your mind force, and one does not want that image to arise because I don't know of any sense that I could attach to the word force in this context.
But in this question of everything interacting, with everything come up in classical physics already. If you want to define an inertial system, then you have to, with respect to all masses in the cosmos.
I think you are right.
So I don't already call that an interaction.
Well, it's the word action and interaction is primitive. When your theory is really well formulated, you will have a set of differential equations, and they will evolve. And whether you say one thing interacts with another, or just drift has to calculate, time drift has to be calculated from the space derivatives. It could be fields rather than objects interact with one another. And the interaction will be a term in the Lagrangian that you will point to.
So let's say the definition of the inertial mass, is that not already a very non-local phenomenon?
Well, I don't know that it is so non-local. Are you doing experiments or theory? In theory, the local inertial system, well, that depends on your theory. In general relativity, it's quite a local thing. Whereas if you tried somehow to build in Mach's principle, it'd be a terribly non-local thing. The local frame of inertia would be determined by the distant stars. But that has never quite been incorporated into general relativity. General relativity permits as one of its solutions empty space, but there is still inertia. So it's obscure. It's having a particular inertial system is like having a particular electric field.
Yeah, but don't you see the problem already there in classical physics without having to go to quantum?
Well, you see the problem that things are not isolated. But in classical physics, the light cones do determine the separation, which is a status in classical physics that it does not have in quantum physics. As soon as you permit free actions, or effectively free actions, in classical theory their consequences are confined to the future light form. And that's a concept that we seem unable to fit into quantum theory.
It seems that we will always have such point because I think the idea behind special relativity is that cones are the essential element defining actions in space-time. And if this is so, that the definition of transmission of energy or of information through space-time is same kind, that together with your result, not in quantum theory, but your result about the maximum of correlation that we can have in local systems, and together with aspect experiment, say, in my opinion, that we will always have some kind of non-locality in this sense.
Well, I think that I agree with you there. But again, the words that we are using are not very sharply defined, so that's why I wouldn't sign what you would write. But it is also my impression that we are stuck with non-locality, that we want to get back to a description in which the different parts of the world are separated by light cones. And yet, I do believe that they will remain separated as regards sending messages. But message is a big concept. You know, you never know quite when you've got a message. For example, when I had those two sheets of random numbers, you saw no message on either sheet, and as I put them together, I could do it slowly and ask you, when do you get the message? So message is not a concept that you can use sharply in mathematical physics. And yet somehow we have to get into the theory the fact that we cannot send messages faster than light, even if it doesn't have a sharp limit.
So I would like to go back to these hidden variables. I have heard sometimes that hidden variables were ruled out, more or less. So I would like to hear your opinion. Is it possible to give some experimentalists who usually give confidence levels for new particles? So could you give some kind
Confidence
of confidence level for hidden variables?
Well, they are not ruled out. That I would assert absolutely firmly. I should moderate it and say, I do not know of any way of ruling them out. But then I have followed reasonably closely this discussion for quite a time. And all the attempts that I have seen to rule them out are fallacious. There was once a famous theorem by von Neumann, and one day I'm going to write a history of it because it's a very interesting psychological study. Von Neumann, around about 1932, I think, made a proof that Einstein's conception of hidden variables couldn't possibly work. And repeatedly until about 1952, you find the great men like Heisenberg, Bohr, Pauli are saying von Neumann has closed off this line. And they never read von Neumann, not one of them, I'm convinced. But sorry, go on.
No, but I think the question was different. I mean, what if I would interpret you now literally, would say all the experiments were done have no meaning because you always can reinterpret them. I think the question is, if you make certain assumptions, for instance, if you assume you have locality,
Right.
then the question is, what does it mean that your theorem is valid or not valid?
Right.
And that has been shown by experiments.
Right.
And the experiments certainly have an error.
Right.
I think the question was, under definite assumptions, you can interpret the experiments,
Right.
and what are the experimental errors then?
Right. That was your question. Okay. Now, the experiments are statistically very significant. So it is in the systematic errors that the doubts arise. And the systematic doubts are enormous. And there is a school of thought which exploits that fact and goes on talking about local hidden variables. There are experiments which you could imagine excluding local hidden variables, but they have not been done. The experiments that have been done are deficient in many ways. The most easy one to tell people about is the efficiency of the counters. The counters are only about 10% efficient. So you see, on nearly every trial they say no, and very rarely yes. And in such a situation, the inequality is trivially satisfied. So you have to extrapolate from this practical experiment to a more ideal experiment by correcting it. And that's a theoretical adjustment of your experimental results. And it is only the adjusted experiment which becomes critical. Now, you think that's an innocent sort of adjustment? Then there are others. In the ideal experiment, the two photons come out in opposite directions, going in prescribed directions. But in the real experiment, they come out in all directions. And that also causes the counters to say no nearly all the time. So again, you have to apply a theoretical correction to what would happen if you could direct the photons in the right direction. And there are many things like that. Now, the theorist can imagine devising an experiment in which all these loopholes are closed. There would be veto counters which abort the experiment when the photons go the wrong way. There would be 99% efficient counters and so on. And I'm told they could be built, but they would be as big as CERN. So if you want loopholes, you can find them in the experiment. And it's not the kind of thing which can be expressed in a confidence level, because you just have to judge the plausibility of these escape routes.
It's really so bad. I mean, the experiments are not so bad.
They are. They are very good experiments, but conceptually they are very bad.
But in the annihilation photons, they certainly go the right way.
Sorry, which ones?
Annihilating photons.
No, they go in all directions.
Yeah, but they're correlated.
Yes, but that's not enough. Because the no-nos dominate in your counters. If you had veto counters to abort the experiments in which they go the wrong way, so that you didn't count them in your statistics, that would be fine. But when you just leave them to go where they like and pick up what you can get in the way of coincidences, strictly speaking, you cannot use that result to exclude the local hidden variables. If you allow the hidden variables to determine the way the photons go, as well as when they pass or do not pass the polarizer, you find that you can do it.
Is it true? Because I thought you have two independent information. You have momentum conservation, which makes sure that they go in opposite directions.
Opposite, yes, but not necessarily the right direction.
But what if you have a counter there and you find a photon there,
yes,
you are sure that because of momentum conservation, the other one will hit the other counter.
That's true. You are right, and I was wrong in what I just said. So that if you did it with annihilation, say pi into gamma gamma, you would have overcome that difficulty that I mentioned, but sometimes they go in the wrong direction. Now, the experiments that have been done with annihilation have not been done with pi gamma gamma, but there is positronium going into gamma gamma. But then you have other problems, namely that for photons of that energy, you don't have strips of polaride or anything like that. And you analyze your polarization by Compton scattering, and it's only a statistical check measure of polarization. So instead of yes, no, you have maybe yes and maybe no as the outcome of your experiment. And again, there's no inequality in that situation. It's only for optical photons that you have good polarizers. So that for optical photons, the polarizers are as near perfect as necessary. Then the counters are inefficient. And then moreover, it's a three-body situation because your atom still can take most of the momentum and the photons do not go back to back.
That's why we're getting into technical detail. But that I don't understand, because in principle, it should not matter whether you use a quantum mechanical in quotation mark polarizer or a classical one like your foils, because in principle these are also quantum effects.
Oh, in principle there is no question, but in practice there is a question. To get my inequality as a consequence of, to get my non-locality inequality, I need yeses and nos. And if the sharpness of the decision is diluted in any way, you spoil it.
I don't believe in the correction for the efficiencies.
No, people have devised models in which no, you see, we tend to think that efficiency is just a matter of a percentage and that we get an unbiased sample, that the things which penetrate are an unbiased sample of the whole set. But people have devised hidden variable models in which the efficiency is a function of the hidden variable. And all we measure with our experiments is the average over the hidden variables. So it is quite easy to construct models exploiting these loopholes. Now, usually I am in a company which, where I then have to say, the experiments convince me, and they do. But those people who look for loopholes can find them.
That's a question, another question, philosophical nature. The question of mind and perception. And some months ago, Wheeler, in a talk in Zurich, said to me that he is convinced that a fundamental role played by the observer. also insists very much that mind is a central element of the theory. Because of the fact of non-locality, it seems that mind, if any, which constructs the observed world, if a mind constructs the observed world, this mind could not be alone the mind of the human observer.
Well, if 2 and 2 are 5, what is 3 and 3? I simply do not follow Wheeler and Wigner in saying that atomic physics involves the human mind. I see not the slightest trace of the human mind in atomic physics. And here I am with Bohr rather than the others, although many times I'm against Bohr. Bohr insisted very strongly that the only observer that he was concerned with was the inanimate apparatus. He was insisted that you could not separate atomic processes from the apparatus that was used to amplify those processes onto our scale. But then he insisted that whether somebody is looking at the apparatus or not doesn't matter a bit.
Yes, but he says that this is all right, but because different observers will always see the same.
Yes.
In this conception, objectivity is granted. But I think his opinion is that the phenomena occurs in the moment in which I am observing.
That is not Bohr.
That is not Bohr.
No, that may be Pauli, and it may be von Neumann and Wigner and London and Bohr and Wheeler and a whole host of people, but it is not Bohr. And I think that Bohr was the sound person on this. It's an enormous extrapolation from the situation in physics to the idea that the human mind is involved. Now, I can see the motivation for that extrapolation. Because when you say the apparatus is playing an essential role, you are asking, well, how do we divide the world into systems and apparatus and the rest? And it's clear that any such division is a very shifty thing. So people look for somewhere that a division could more naturally be made. And they say, aha, between matter and mind. And so they postpone the so-called reduction of the wave packet, which is an element of ordinary quantum mechanics. Instead of that occurring in the apparatus, they say, let it occur in the mind. But that's a conjecture, an extrapolation. There is no evidence in physics for that. As far as physics is concerned, it can all end at the apparatus level.
Where does it happen? Sorry, where does the reduction of the wave packet happen?
Well, it depends on your theory. Now, in conventional theory, they don't say where it happens, and they just exploit the fact that there is such a big difference of scale between atoms and apparatus that you don't have to be very definite about where it happens. But there are theories now which say exactly how it happens. There are equations, and the nicest of those theories is due to some people in Trieste, Girardi, Rimini, and Weber. And according to them, wave packet reduction is happening all the time, even in the hydrogen atom, but not very often. And in a big system, it is happening 10 to the 23 times more often than in a hydrogen atom. So in big systems, they always are classical-like in being in definite states, where little systems are not. So there are theories which tell you where it happens, but they are going beyond ordinary quantum mechanics.
What has to happen with faster than speed of light?
Yes, and it's very interesting then to see whether it can nevertheless be consistent with relativity theory. And there are some hints that it can. But it's very subtle, and I don't know in this audience whether I can go into many time Schrödinger equations and things like that. But there are some studies in that direction.
Well, reading your book, I have get the strong impression that what you tell us is that the real cause is mathematics.
The real
The real cause.
cause.
The
Right,
real
okay.
cause
Sorry.
is mathematics. The mathematics that determines what is happening in the world, and the real principles of reality are these wave functions that from somewhere are working on the observer's world. This impression I have get very strong, and I want to rely that with the last talk by Professor Chopper, that if you analyze what are particles, in the last term you say particles are mathematical properties. And from the philosophical point of view, the big question which arises here is, where is this mathematics content? If the mathematics plays so a big role in this kind of models, and it is not a mathematics which is localized in the three-dimensional space, but is in infinite space, in abstract space. Well, the question which arises, where is this mathematics?
I don't know if you asked where is the wave function. That would be, to me, a question that I could think about. But where is mathematics?
Yes.
In a more general sense,
More general,
mathematics
yeah,
with a capital
exactly.
M.
Yeah, that is it.
Well, I don't have a clear final opinion on that, but my provisional opinion, which will probably last me the rest of my life, is that mathematics is a language. Now, do you ask where is language? It proceeds out of our mouths. But does it have to have somewhere, a sort of heaven where it exists by itself, so that you can ask where is language?
No, these are exciting answers, because the problem is that in our cultural tradition, language is inseparable from mind. That is, you cannot have a language if you don't have some kind of mind. And that is what I feel, what people as Wheeler and as Wigner feels, but they are limited to the human observer, and in this kind the model cannot work. But you should suppose, like what the cultural tradition have made, that you have a lot of very big intelligence, suppose like angels. Angels could be computers, for example. In this model, mathematics are a kind of language which some intelligence is speaking to you.
You want to go in the direction of Bishop Berkeley. And,
Oh.
and I am sympathetic with that because Bishop Berkeley was an Irishman, but for no other reason. You see, it seemed to me that his process of reasoning was like this. Nothing can exist except ideas, because really we have no direct knowledge of objects and so on. We just have ideas. So only ideas exist. Then he was discontented with that. And so he said, but it's God's ideas that really exist. Whereas for me, the logic is this: nothing exists except idea. Therefore, God is only an idea in my head, because I have no way into the head of God. So if I locate everything in my head at the beginning, God also is there. And that is not the conclusion that Bishop Berkeley would have liked. So I think that you have to jump out of your head and have a concept of reality. And Whether that includes God or not is a matter of taste.
Yes, all right.
I don't see any logical necessity.
No.
So you could say where the wave function is.
Absolutely, that's a smaller question.
Where is it?
Well, the wave function does not live in ordinary three-dimensional space. In the case of an n-particle system, it lives in a 3n dimensional space. It's just a function of that many coordinates. So somehow our feeling that we live in 3 + 1 dimensions is an illusion. It's a very persistent illusion, and it's a very important thing to see how is it that although the wave function lives in 3n dimensions, we have this feeling that was mentioned in the song that I wrote there, that we are isolated in 3 + 1 dimensions. And we don't have an account of the subject which makes it reasonable. That's my opinion. It's the same dilemma that I mentioned.
Well, look, I think we're back to the old question. Either you take the strictly positivistic point of view, where you say all we want to do is find rules which connect different measurements and so on, and you don't care what all that means, which I think is not satisfactory from a human point of view. If you go beyond that, you have the problem which exists also in artificial intelligence or languages. I mean, language as such is a set of rules of grammar, syntax, whatever you have, and that you can teach a computer. So you can say you can teach a computer how to speak Chinese or whatever you want. But in the normal sense of the word, we would not say that this computer understands Chinese, because the essential element comes in which goes beyond the syntax, which is the semantics. The computer will handle concepts like table, chair, and so on, but still he will not know what a table is. And that's where the point is, where the formal abstract rules are somehow connected to the real world.
Yes.
In quantum mechanics, it's kinds of observables, which connect the wave function or the symbolic things you have with reality, but which brings in this reduction of the wave function and things like that, which I never understood. But I don't understand, even if I go to language, what is the difference between teaching computer the syntax and telling me at the same time the semantics. That's why people can never agree what artificial intelligence is, I think, because that's also the difference. That is a key point. I don't know the answer. But what means to understand something, the semantic understanding. And whether that is just a matter of complication, I mean, is because our brain is so complicated and has so many synapses, does a mere complication bring in this extra quality, or is it something else?
Well, I don't know the answer to that. I think that's a very intriguing question. At what stage does consciousness arise in the physical system? And I have not the least idea. And I must say I have read at least a dozen books on the subject. And I formed the impression that nobody has any idea about this. So coming back to this question of the role of mind, I do not want to minimize the mystery and importance of mind. I do want to say, in my opinion, there's no sign of it in atomic physics. But that leaves the rest of the world still.
No, but I think, from what I say, you would say there's no sign of it in the syntax of the atomic physics. But if you say atomic physics is more than just an abstract invention and has to do something with reality, then you have to bring in semantics and then to bring in the mind.
Right. I would still maintain my position that there is no sign of mind in atomic physics. That the conception of atomic physics, which we all use in our working lives, simply does not have mind in it. Now, that may be because it's a narrowly selected range of phenomena that we are dealing with. And I do believe that that's the fact. I can think of nothing more important than mind in my world as a whole. But I do not believe we have got to the point where you can see a kind of unity in our legitimate conception of the world. So that mind, which is very important at one end of the spectrum, is already relevant for the spectrum of the hydrogen atom or something like that. Now, I do not exclude that as a possibility that it might be like that. But when I look at atomic physics as I know it, and as it actually works, and as the physicists use it when they're not philosophizing,
But you have to explain what an observer is.
Sorry?
How do you explain what an observer is?
No, but then that is a little more technical. I would show you this Curardi-Rimini-Weber theory. It doesn't need observables.
You have started saying that the situation is not satisfactory.
Sorry?
You have started saying that the situation is not satisfactory,
That's for
not completely
sure.
understood.
That's for sure.
So could be that just not taking the mind into account is the reason for not having an explanation.
It could be like that. It could be like that. But when I look at what has been successful in atomic physics, and it has been immensely successful, in my opinion, it is just imagination and poetry that allows people to see anything mental about it. So there are different things in different parts of the world, and all I'm saying is that I see no connection. And I do believe that those great physicists like Wheeler who go around the world saying that somehow the lesson of the quantum is that the world must be observed to exist. I think he's being irresponsible, and I have told him so. But he goes on just to say.
Please. No, if you have the last question, because I think we must come back to the local.
Yes. No.
Well, in this same question, well, in this case, Professor Bell, we are most grateful to you because I think all of us want to have such a discussion with you. Thank you very much.